Welcome to the talk on designing MLOps systems. And today we'll be talking about a big picture first. What is MLOps? And what does it actually mean? And then we'll look at the nuts and bolts that make up the entire system. I also want to share from my implementation and consultancy experience the common mistakes that I see, and also the common design principles that we can uphold when designing our own MLOps system. So this talk, I hope, will empower you, regardless whether you're experienced or beginners, to walk away with knowledge and also confidence when you think about your own big picture MLOps system design. So a couple logistics. I will leave Q&A time at the end. So for the in-person attendees, please raise your hand if you have a question, and Mary Grace, our moderator, will walk up to you with a microphone. And for the virtual attendees, please feel free to leave your questions on the platform. I'll make sure to check them latest by tomorrow night, and I'll get to your questions. And all the slides will be posted at the end of this presentation as well. So you don't have to take any pictures. You can definitely have the copy of the slides after this talk. A little bit more about myself. My name is Cheng Yin. I'm a senior data scientist at Databricks. Been here for about 3 years. My focus has been on building scalable end-to-end ML pipelines. And my bachelor's degree was in statistics and environmental science, and my master's degree was in computer science. So let's dive in. What is an MLOps system? When you think about MLOps, you might already hear about the term DevOps, which is a really common and long-standing practice that combines software operations and also IT operations as well. So if you know that, then your intuition will already inform you what is MLOps. It is a discipline that helps you to push your model to production and then maintaining these models post-production and ensure that these models are successful in the long term. So it also means that an MLOps system doesn't just contain one great machine learning model. It contains all of the pieces around it that supports this model and supports it to build this iteratively as well. So it is about the data, the infrastructure, the feature engineering process, model evaluation, the production, and also the post-production concerns. So how do we start? By looking at evaluating what is a good MLOps system. There are 4 main criteria. First is reliable. It means that you have to ensure that the predictions are always consistent and accurate. And if you were to push this model to production and it fails, you better have a fail-safe plan as well. The second component, it is scalable. This probably is a no-brainer. We have to think about supporting not only high workloads, but also low workloads as well. Third, it is maintainable. It means that we prioritize maintainability over complexity. We actually think about how do teams actually collaborate effectively. And the fourth, it is adaptable. Your MLOps system has to be able to adapt to changes, business requirement changes, and also changing market requirements as well. I want you to leave with one takeaway if you forget everything else that I said. A model is not the product. You are using so much more than just the model. It is the system that is the entire product. It is each nut and bolt that we might have neglected for too long, and then a technical debt starts to chase after us. So let's talk a little bit more about data. When we think about designing MLOps system, the most important thing is to adopt a big picture thinking framework. It means we consistently think ahead about the downstream usage. And that goes the same way for data as well. So we may choose to actually have more efficient file formats. So for example, if you know that you're going to repeatedly query the data set, but only for a subset of features, then use something that's column-oriented. For example, Delta or Parquet. So this also allows you to maybe think about how do you actually store data with partitions? Then if you were to have a lot of querying by filter statements on different subsets of data, how can you actually further optimize the performance? So this is where I highly recommend you checking out the open source Delta Lake storage format, which has built-in optimizations that help you with your downstream performance. Secondly, splitting data into training and test set. This is probably something that we have struggled or already known for a really long time as data scientists. We know that we should split data. And we know that data quality is the very first component that ensures that you have a great quality model as well. But how do we do it? Do we always do it by random test train split? Well, if your model is time dependent, then split by time. Secondly, we should split before we scale features. Same goes to imputation as well. So this is really important because when we split after, if we were to split after scaling features or after imputation, it means that we're actually injecting the overall data summary statistics into the trained data set that we don't want to bias. The last point over here is to check for duplicates before splitting. And you might think, again, this is a no-brainer, but you might be surprised by how much this actually happened in real life. So an example that I can give is CFAR 10 and CFAR 100 actually have a lot of duplicates, 3% and 10% respectively. And think about the grand scheme of how this actually affects how we select models. If the duplicates contain like overlapping at 10%, then it means that the selection of model can actually be different. We might actually choose a different model to push to production. Next is data versioning and testing. So thanks to software just being around for a really long time, we have been really used to the idea of testing software code. But we need to apply the same principles to data as well. Treat it as an asset so that we can actually detect early inconsistencies. Keep track of data versions. Maybe all of us have been using file names. I've definitely been there. Use the month, update the month at the end of the file names, and I realized that eventually I may forget what I actually wrote. So you see that this is actually quite cumbersome and not really robust. So let's use something that automatically does that for us, Delta. Data versioning is really important, especially when in production, we never really know what goes wrong. So if we were to need to debug the production errors, and it might due to data issues, then this is a really powerful feature that we can leverage, delta time travel, to actually compare between data versions. And you can see here that you can either compare by timestamps or by version numbers. And also, it's more than that. It's also about the schemas as well. And schema is typically referred to as a list of columns and also their respective data types. So we need to actually check if the data types actually match with each other, and if we actually do have all of the expected features when we ingest data. Again, this is where Delta comes in handy. I personally really like the feature that we have. Delta is built-in schema enforcement functionality. So if I need to override changes, override data, I actually need to pass in an explicit argument that says override or append. So now that we have talked about data, let's talk a little bit more about the features within the data. The top myth that I would think that happens very often in real life again is we think that more features are equal to a better model. And I want us to start shifting our thinking towards relevancy and maintainability. A high number of features usually leads to model overfitting, and a large model size also means that you're increasing a model latency requirements as well. And over time, you're just incurring more and more technical debt, and you slip on your own technical debt here because you have to maintain so many useless features that you probably don't even care about at production, and that but probably don't even bring you any business values. So aligned with that, let's also think about feature importance. And I also want to emphasize that this is not just a simple tool you can throw at, let's do XGBoost, random forest, and then get the built-in feature importance, and that's done. We should think about feature importance much more early on. When we start even building the model, let's involve the subject matter expertise to talk about what do they expect to be important and what do they expect to be not important. It's possible that all of us might not know everything, but at least having that baseline understanding, we'll be able to compare what is aligned with our expectation, and if something doesn't, then we can investigate. So let's use our intuition to actually guide our ML building process. Of course, then that involves data exploration, which is probably the most time-consuming part and probably something that we would like to skip if possible. So we always look for the automatic ways to examine the data exploration and look at the correlation. But by all means, as long as you know the relationship between the features and target, and also correlation between features as well. So here are some tools that you can use. The built-in feature importance, SHAP, Lime, FairLearn, Interpret ML. Next, let's also try to reduce feature engineering effort to allow consistency and also reuse. So here is where we might actually want to think about adopting a feature registry, or also what is commonly called a feature store. Informally, I think a lot of organizations have already done this. Like we may actually designate a specific storage path and say, hey, let's all designate our feature tables, store them in this specific path. I think that might work for some small organizations and for a really small team with great agility and great collaboration. But in a bigger organization, we might actually want to think about a formal product for just feature store. So this is what one example of a feature store can look like. This is a Databricks feature store screenshot. So you'll be able to see that this table contains how many features, 21 altogether. I can easily see the data type. I know exactly what models are using them. I know exactly if I push them to the model to a REST endpoint, which endpoint is consuming the features, the jobs, the notebooks. So you are able to track how are you using these features. So this means that your team can easily discover the feature tables and also the feature names. An added advantage is that you can avoid the skew between training time and also serving time, because now you do not have to duplicate the feature engineering process at both separate points on time. Now let's finally talk about models. This is probably the most exciting part that all of us are really excited about as a data scientist. In my opinion, the single most important principle when thinking about models is to start simple, and is to think about iteration as your best friend. So you can see this inverse pyramid on the slide over here. We tend to rush to classical machine learning or even deep learning models without really thinking about baseline model. So a baseline model could really just be a really simple model that's completely rule-based. It's super easy to build. It's really fast to build. And you can then easily prove out your idea. Do you think this business idea is worth pursuing, and then converting that to an ML project? And similarly, we also really like to use hyperparameter tuning, especially for complex models like deep learning. But I will also caution that let's not rush to that process, and make sure that we evaluate simpler models with just enough attention as well. If you train a deep learning model or tune a deep learning model with 100 hyperparameter combinations, and maybe it finds the best hyperparameter combination at the 99th trial, but you only train your simplest model for once, then that is not a fair comparison. We should also check the model assumptions as well. This is where statistical understanding of algorithms and also connecting that to data exploration is really helpful. So then you can actually check if your model is actually, your data distribution are violating any assumptions about the model. And then you can early on already tell that, well, this model is not going to work because it violates the statistical assumptions. Lastly, we should also just build single node models first, especially if the data is not big enough or just small enough to fit on your single node, and then only attempting the distributed implementation. So in other words, iteration is your best friend, and keep things simple. Another common mistake or the mindset is to chase after the shiny stars. I think this is a really common trap that all of us fall into, especially when we read about a really great industry or academic paper that talks about how we can do these things better and faster. But it's really important to remember that applied ML is very different from research ML. In research ML, we don't really know whether the data looks alike with our production data. That's only the first thing. And the second is there even community support? Are you now going to dedicate like 10 people or 5 people to work on this one implementation for 1 year or 5 years to replicate something that people have done for years and for years, and now you're going to expect like great stable stability in your production system? So that's not going to happen. So similar to data, let's also track and version the models as well for better reproducibility. We are probably really used to tracking hyperparameters, evaluation metrics, artifacts, but we should also think about the environment. Like if all of us are working on different laptops, just building models locally, I don't really know what package versions we are using. So to make sure that there's compatibility and also make sure that there's consistency across environment, this is something that we should tackle early on and not just wait until we have to push the model to production. So make sure that if you have different environments, you think about the package versions or use a cloud tool to help you replicate the same environment. And this is also especially important when you adopt a containerization approach as well. And I also want to emphasize the class imbalance ratio point under the evaluation metrics. So we know that the model does great, but do we know if we were to build an imbalanced classification model, how is it going to behave if that imbalance ratio changes? So that is something that we would like to know as data scientists as well. So here's an example of the ML Flow UI. So you can clearly see that there's parameters, metrics, user-defined tags, artifact section where it has the whole model object and also environment details. Now that we have a model, let's push it to deployment or deploy it to production. So deployment consists of two tightly coupled steps, testing and release. So you can think of this as an iterative process as well. If a test were to fail, you cannot release it. And if it doesn't perform well in the release stage, you need to go back. So model testing is definitely a very cumbersome and very time-consuming step. So I would recommend to write up a checklist first. What is required and what is nice to have, so that you have that overall requirement and big picture thinking again to guide you in your writing test, the workflow. So you may be testing on key metrics. You may be testing on random data points. You may be conducting unit tests. And there are also post-training tests as well that you can try. So here's just a few examples. There are many of them out there. So just pick one that's most relevant to you. So the first one is invariance test. So this is important or relevant in the context of data augmentation. Do we know if the augmented data is actually behaving the same way or affecting the model output the same way as the original input data? If I were to switch a cat image upside down or slightly rotate the angle, then my object detection model should still tell me that it's a cat. The second test over here that we can consider is a minimum functionality test. So this is something that is just a gut check to make sure if the model is performing well. So let's provide some really simple inputs to the model and check if the model outputs actually make sense. And say, for instance, if I have a translation use case, I may be providing a really short sentence, maybe 2-word sentence or 3-word sentence, and I actually see if the translation is actually correct. The third is directional expectation. This is my favorite because I think it's really intuitive. If we were to change the direction of the model input, if something were to change from positive, negative, and vice versa, is your model output the same, the different? So if that is not within your expectation, you should also double check if that model is indeed as good as you thought. And here's an example too, which is deep checks. Now let's talk a little bit more about deployment methods. There are also a variety of deployment methods over here, but before we dive into what are the possibilities, I want us to also think about a fail-safe approach. If your model were to fail at production, what should it do? Could it be maybe leveraging the last model? Could you actually be maybe writing a really stupid model and output a prediction? So for example, if your recommendation model fails and it just doesn't output any more recommendation, and someone goes to Netflix or whichever streaming service, what should be the output that you see? Could I actually maybe hard code a few movies so that it's not actually blank or says error? So those are the behaviors that we should think about and what is acceptable to present to users. So let's talk about the first method of deployment, which is shadow. It's one of the most common one, which means that you deploy in parallel with the existing model. But that shadow model actually doesn't do anything to the end users, because we're only serving the existing model's prediction. The second is A/B deployment, which means that you deploy in parallel, but a new model actually serves a percentage of traffic. So take a look at this after plot over here. So you can see that V1.2b serves 70% of the users, and then V1.3d serves 7.3% of the users. So you can see that it's version 1.2, version 1.0, version 1.3 serving at the same time. The next deployment method is canary, which means that we're rolling out incrementally to a subset of users. So that is slightly different from A/B. So you can see that for canary, we're actually increasing the proportion of users that's actually actively receiving the new model's prediction. Last is interleave. We show both new and existing model predictions. This is also especially relevant in the context of recommendation model. It's possible that we never really have ground truth. How do we know which movie are we going to watch tonight until you actually watch it? So maybe the best thing is to actually test out both models and then see how users interact with your outputs. The next component in ML system is to think about monitoring, observability, and retraining. And I also want to emphasize that monitoring and observability are not the same thing. And retraining itself also has a lot of nuances as well. So this is one topic, I think, in the MLOps system that's very quickly evolving. So I think this is a really promising field that we can all watch for updates. So let's talk about monitoring. Monitoring typically means that we know what conditions to expect. Therefore, we pre-declare those conditions and then watch for them. Therefore, we often call them as the known unknowns. So one type of monitoring that we can do is data drifts. Probably have heard about it a lot throughout the whole day today. It actually happens more than we assume. It's not just a black swan event, that the COVID pandemic that we're going through right now. It could also be something like influencers just promote your product. Now your product popularity spiked. But is that popularity going to last? We don't know. But is that a drift? So there are many types of drifts over here. First is feature drift. Feature drift is referring to the deviation of the input data, or the input features, from the original baseline data. So keep in mind that drifts, whenever we talk about drifts, we're comparing against something, against a baseline data, against the original training data, or maybe even a trusted set of data. The second type of drift over here is label drift, which is the ground truth label. That is provided by the market, by the system for us, what is the label. The third is prediction, which is our model output. The fourth is concept drift. This is, I think, something that we can all really grasp very well by now. So when we think about COVID pandemic, and if you refer to the image on the right, we cannot really tell which phase are we in right now. Does COVID actually have the sudden behavior of becoming, changing from better to worse, or is it a gradual change to worse, or is it an incremental change to even worse, or is it recurring? So concept drift is often something that's really hard to tell what is going to happen because it's entirely dependent on the market. So it means that it's really important for us to establish a baseline data. And this is something that should be entirely trusted. It means that we have closely vetted it and know that this should be how the model is behaving based on this data. And therefore, when we actually see drifts like in performance metrics, we know exactly that we can trust the metrics. Why? Because the data is vetted and trusted. So I will also encourage us to go beyond just looking at aggregate metrics, but also looking at the metrics on subsets or even slices of data. Because the aggregate metrics often is good enough, but that is not good enough for us to be able to tell the non-benign shifts. So you may notice that I'm using the term non-benign. So it means that on the flip side, there's also a benign shift. In other words, data drift can actually be quite a hard thing to tackle because we oftentimes do not know what is the right course of action. Because maybe the right course of action is to simply wait it out and do nothing. And it might not actually be retraining or even building a new model. And this is, again, something that will rely on the business expertise to actually decide what should be the appropriate track. And when we monitor, we should also monitor the business KPIs as well, in addition to the regular model metrics. And let's also monitor something about infrastructure. Has the prediction volume changed? What about the system uptime and downtime? How are we actually using our cluster and compute? So usually, monitoring manifests itself in one of the three forms over here. You have a lot of metrics now. You aggregate them into some form of dashboard that you can easily present or share with people. And you may set up alerts if your number actually passed a certain threshold. So these are all pre-declared. It means that our ability to troubleshoot depends entirely on how we're able to predict the errors. And that is how it is different from observability. Observability, the concept, actually comes from the field of control system theory. So the premise there is you can infer the state of the internal system based on the external outputs. It means that this helps us to actually understand what leads to a novel failure mode, even if we have never seen an error before. It allows us to observe all of the possible behaviors that a system can exhibit. It is much more fine-grained than monitoring because we can reconstruct the circumstances based on the output. So the output can look like your metrics again, your stack traces, or even logs. So the logs here should have high cardinality or high dimensionality. You should log as much things as you can, this is especially important when in today's world, we're not just deploying a monolithic service. We're using microservices architecture. We are distributing our machine learning workload. How do I know which container, which service is actually throwing that error? And that is something that we need to keep track of. So this is more than just a tool. Observability is social technical. It means that it relies on culture scaffolding that actually supports the process and hosts the process that determines how your process is being developed, tested, debugged, and also maintained. It means that observability has to be within every single component in the entire system. It's not good enough to just have observability into one tiny thing when you actually want to look at all the possible behaviors that an entire system can exhibit. So this is what happens if we don't pay enough attention. We might miss things that we never know. So let's talk a little bit more about retraining. I want to challenge us to not use a simple approach and do a blind retrain. Think about the nitty-gritty. How, what data, and also when. How? Should we train from scratch? When we have new data, especially when it's a deep learning model, should we just train the model on existing the new data? It means that we're leveraging stateful training. What data? Do we actually retrain based on the entire data set, or do we retrain before the data has shifted or after the data has shifted? So there is really no clear answer to this, and this is, again, where the business expertise can come in handy. And the last question over here is when. You can do a manual trigger, you can do a scheduled trigger, and perhaps you want to automate this, and you actually are retraining based on metrics, performance-based, when maybe your R-square has dropped, volume-based. So this is important in the context of imbalanced classification model. If now, all of a sudden, you have just a batch of all of the minority labels coming in, then it's actually really important to retrain first, because that can actually dramatically improve your model performance. Or especially since when there is a large batch of data coming in for your minority labels, then it can actually maybe make the model to behave differently. And lastly is the drift-based metrics. I want to emphasize and highlight enough that human oversight is really crucial. There needs to be a human in the loop. As much as we would like to automate everything to make our lives easier, it is simply not possible. Case in point, if I were to have bad data ingested, and then I retrain it, guess what I'm going to get? A bad egg. And what does a bad egg do? What does it taste like or smell like after overtime? It smells bad and it smells worse, and then tastes bad too. So we don't want to avoid that. So let's talk a little bit more about the workflow and resource management. And this is definitely a really large question because it is about our infrastructure. And if there's one thing you need to know about infrastructure, it is this. Your workflow should guide your tooling and infrastructure decisions, not the other way around. What is the overall workflow? Have you thought about that before you start an MLOps project or any ML project? Do you actually want to use a model store, a feature store? What environments do you have? Which environment do you want to conduct testing on? Resource management. If you were to build a really fancy deep learning model, can your company actually afford to deploy that for over the long term and actually maintain that? And it's not just maintenance. It has to be reliable, and it has to enable your team to continually innovate upon it as well. Do you want to use containers? Do you want to build your own solution or buy existing product? So all of these answers might actually depend on your specific team needs. And lastly, the job orchestration over here, we have a few options. We can trigger jobs based on the drop of artifacts, the schedules, or maybe based on a code change to Git, or maybe a manual REST API call. So let's wrap up. I hope you understand and you see by now that MLOps system is big. It's not just a tiny, tiny machine learning model. It is all the pieces that surrounds it, that supports it, that enables it to actually function well over time. It has to be reliable. It has to be scalable, maintainable, and adaptable. A model is not the product. It is the entire system. So let's walk away with some best practices. Documentation. This is probably we have a love-hate relationship with documentation. We like to have them, but we often don't write them. So I would really encourage all of us to put as much attention to documentation as you would to build a great model. After all, this is the only thing you have if someone were to walk away. And modularize code. Don't leave commented out code in your production code base. Emphasize maintainability or simplicity over complexity. So it means that if there is one line of code that you can do everything in one line, but it's not readable, break it down. Do your coworkers a favor and write it in multiple lines so that it's more readable. And even SQL formatting matters. I bet none of us here wants to read a really long, ugly-looking SQL code without any formatting. So let's also pay attention to how we write them as well. The next is to be tool agnostic. And this again goes back to the infrastructure decisions. We don't want to be fixated on a specific tool just because it's popular, it sounds really great, and it probably gives you a lot of credibility on using it. But let's use our requirements to define our decisions in infrastructure. And let's also think about trade-offs. Nobody's perfect, and no MLOps system is perfect. It means then we have to think about what we prioritize the most, and then give most attention to that component, and make sure that you know what you are sacrificing when you have a specific decision to make. Next is to conduct regular architecture reviews to address your weak spots, track and version any of your code and models, data, including data as well, and also be truth-seeking and blameless if something were to go wrong in production. Nobody wants to be pointed at. So let's just uphold the principle of being truth-seeking. Few resources I would like to leave with you. Here's a list of big picture questions that I personally always use. Think about the data, the code, what is the model impact, why do you even build it, what is the model latency, etc. And also think about what is the best way to actually help your data scientists to work as well. I personally don't really like 2-week sprint because my actions, my tasks always change depending on my data insights. So I often find that I have to go back and rewrite my Jira tickets because of what I saw. So I personally prefer to have a much shorter sprint, especially when we're dealing with data. So here are some references that I can leave you with. The first 2 books are both this month. the engineering MLOps book was released just last year, and there's a great blog post about the data science and also agile workflow. Then the rest of the books I can leave you to it. I think it's already a long list, and there are also a lot of other MLOps resources out there. My slides are on this link. Feel free to scan the QR code if you want a copy of the slides. And before I start taking any questions, yes, the QR code is still there. If you need to leave the room early, please just make sure that you leave the room silently and leave all the chatter outside so that the in-person attendees can still enjoy the conversations. And for the virtual attendees, I will make sure to log into the platform by tomorrow night and also take a look at your questions as well. So thank you all for being here, especially since it's the last talk of the day. And Mary Grace will be walking up here. If you have a question, feel free to raise your hand.
Thank you for the presentation. And I'm quite new to this machine learning and data science, so this might be a silly question. My question is that when you were in a situation that you need to do the retraining, is there cases that like you actually go back to the feature engineering and then need to come up with the new features? And then if there's the type of the cases, like from your experience, like how often it is?
Yeah, for sure. So the question is regarding whether there are any principles that we can look at when we want to retrain a model. So I would say the first thing is to actually think about what may be the underlying reason that the metrics have shifted. So for example, if you know that the metrics have shifted because of a changing market, then a blind retrain may not actually just solve the problem. You might actually need to revisit the entire model development process, which means you are maybe going back to cleaning data, engineering your features, and create even more features, or maybe even thinking about an entirely different approach. So you're absolutely right that retraining is not the answer to everything, and it often is the intuition and the business expertise that informs us of what should we do if the performance metrics were to drop.
Awesome. I think we are at time, so if you do have additional questions, I know Chang will probably hang out at the front of the stage. Thank you so much for coming, and hope to see everybody back here tomorrow.
Bye, everyone.